today we will continue on. So, we have covered linear regression, logistic regression, and now you understand Anova actually is what? Is a linear regression problem. It is actually a linear model, right. So, we will go back, revisit Anova in terms of linear regression approach and then move on, okay. And then we will refine Anova. Remember, in Anova we did not include interactions, okay. And the other thing we haven't talked about in Anova is, I do not know how many of you. So, remember we had noise as one factor and treatment as another factor, but many a times there will be other nuisance factors as well apart from noise. Let us say if you are doing with study with respect to a population, then the gender will become actually a nuisance factor, right. You would want to work it for both the cases, but somehow you might have tested only on one set of population or one group. So, there are factors called nuisance factors which will start influencing your outcomes as well, okay. So, how to block these nuisance factors is something which you have to learn. So, right now we have only considered two factors without interactions, because when you consider two factors there is hardly any interaction, because you have said treatments, you have said noise. Treatment is one variable, noise is another aspect, and by definition of noise we assume that is IID, whatever not modelable, that is what we considered. Now, there could be treatment, there could be other factors which will influence your output which you are not interested in, okay. So, that is we want to block them, okay. So, and then there will be interactions between the treatment and the nuisance. So, things get complicated from there on, okay. You could have multiple treatments and multiple multiple variables of interest, because now treatment at various levels is what interested in. Like that you could have multiple factors of interest to us, okay. So, those things we will start looking at, okay, clear. So, now we will come back to talking about the regression approach to Anova, okay. So far we have blindly did this formula etc. Now we will develop the estimators for parameters in the single factor model. So, that is why I said this is now getting better, it is single factor at various levels. There is only one factor at various levels, that is tau is that factor which we are interested in. This tau could be your treatment dosage levels etc. multiple dosage could be your factor and levels could be your various treatment levels, okay. So, we are interested only in one factor, single factor model, okay. I could add beta j as well, beta I as well as another factor of interest or another nuisance factor, okay. So, my model of Anova now if you look at is Yij equals to mu plus tau I plus epsilon ij, and remember our assumption about epsilon is IID Gaussian 0 sigma squared, same as that of linear regression, okay. And now we are going to find out the parameters. How do I start doing it? I have a minimizing the sum squared errors, right, minimizing the sum squared errors. Remember here I have two parameters mu1 tau I to be estimated from the data, okay. Epsilon ij I cannot model it, that is the assumption. So, I have summation of Yij minus mu minus tau I the whole square, and remember it will be a double summation. Why? This is a matrix, this data is a matrix, okay. So, for every level, so tau 1, tau 2, tau 3 you have data, right. So, there are like that up to tau a, and in each one has n samples, right. So, I have a double summation over n and over a to obtain the parameters, clear. So far so good. So, how do I start doing? I am going to differentiate and equate it to 0 like what we did in regression. But how many equations will I have now? How many equations will I have? When I differentiate, will I get 2 equations, 2 unknowns, or how many equations will I have? This is my last function, dou L, okay. Dou L by no mu is one equation, one differentiation, and dou L by dou tau I equals to 0 is another thing. How many equations will I get? How many equations will I have? For the first one, if I differentiate with respect to mu, what do I get? If I differentiate with respect to mu, so 2 times, okay, so I have minus 2 times Yij minus mu hat minus mu tau I minus tau I hat. So you all understand how do I get this? I am just differentiating 2 Yij minus mu hat minus tau I hat because I am estimating them, right, equals to 0. And how did I get minus sign? Dou mu hat by dou mu hat equals to minus dou mu hat by dou mu hat equals to minus 1. So I have minus 1 in front, double summation, this is equal to 0. This is one equation. What about the other one? I differentiate with respect to tau I, okay. So then what do I have? I have to expand for every I. So how many equations will I have? I will have for every I equals to 1 to A, I will have A equations. Clear? I will have
linear regression, like we have theta and x, the coefficient matrix, and here which are the coefficient and
tau I is my unknown itself. There is no regressor here, meaning in your case y equals to mx plus c, right. So mx, m was your coefficient and c is your intercept or whatever you want to call it. Here I am doing that, but tau I itself is unknown to me. I am trying to explain my output as a function of factors and noise. Noise is not modelable. I am going to explain my output as a function of a constant plus factors. The constant is mu and the factor is tau I. That is, the total entity is not known. So there is nothing called input. The total entity, I am trying to explain the variability in y as a function of constant plus a parameter tau I. Okay, so there is nothing called input here, regressor here, x here. Understood? So I have totally a plus 1 equations. Make sense? For every tau I 1 to a, I will have totally a plus 1 equations. I can expand them, okay, I can expand them. So what do I have? So this is double summation n times mu hat, okay, plus, so I am multiplying the minus sign throughout, okay. So what do I have? Summation mu hat plus double summation tau I equals to double summation Yij. Make sense? 2 is cancelled. Does it make sense everybody? What is double summation mu hat? When you double summate mu hat, capital N equals to a times small n. So capital N times mu hat, okay. And what about tau I? The second one, will double summation work? I, so it is only summated over 1 to small n. So n times tau 1 plus n times tau 2 plus n times up to tau a equals to double summation of y I j. What is this? Overall sum y dot dot. That is my first equation. Is this first equation making sense? Right? In fact, this is what I wanted to ask you in quiz 2. I changed it now because today's class I am taking, okay. So this is how you solve it, right. Your first equation is typically some double summation mu hat plus double summation tau I equals to double summation y. See, double summation y hat is what? Y hat is mu hat is a constant. So double summation means capital N, a times small n, which is capital N. So n times mu hat, okay, and tau I should be expanded for each I. So small n times tau 1 plus small n times tau 2 plus small n times tau A should be equals to the grand sum, which is y dot dot. This is my first equation, clear. And now the other a plus 1 equations are what? So similarly we have what? Summation mu hat plus summation tau I hat equals to summation yij for all j varying from 1 to n. That is my next set of equations. Can we expand on? So what do I have? Small n times mu hat plus small n times tau 1 hat equals to, when I summate only along one axis, what do I have? Y1 dot, right, that is summation along only one axis, right. So similarly I can have summation along y2 dot y dot, clear. So that is where total a plus 1 equations are. How many unknowns are there? We have how many unknowns? Tau i's are unknowns. How many tau i's? A, and then mu is an unknown. So there are n equations and a plus 1 equations and a plus 1 unknowns. But is this a plus 1 unknowns, I mean a plus 1 equations, are they independent? Look at this set. See, you can solve for Ax equal to b when A matrix is, this is Ax equal to b, this is Ax equal to b. You can solve for x only when A is invertible, x is invertible. When is x invertible? Sorry, A is invertible, sorry. Ax equals to b, you can solve for x when A is invertible. When is A invertible? When is the matrix A invertible? Determinant non-zero, okay. Determinant, what is the meaning of determinant? The rows and columns are linearly independent. Are these a plus 1 equations linearly independent? Check. Are these equations a plus 1 equations linearly independent? These are things one should start looking at. This is what, you know, getting into details is. So look at this, if I add these a equations, what will happen? You will get the first equation, right. If I add this a equations, small n times a times n, you will have capital N mu hat, n mu hat, n tau hat, n tau 2 hat plus n tau a hat. If you add y1 dot plus y2 dot plus ya dot, what will you have? It is grand sum y dot dot. So these a plus 1 equations are not independent, there are only a equations, although it appears a plus 1, really only there are a independent equations. So then how do I solve it? Remember we had a constraint, summation tau I equals to 0, that is where the catch is. So our a plus 1 equations are these a equations plus a constraint which is summation tau I equals to 0. Now you have a plus 1 equations, a plus 1 truly independent equations and a plus 1 unknown parameters, you can solve for it. You see the point? Remember when we started with the Anova and fixed effects model, what did we assume? Summation of tau I equals to 0, right, because mu plus tau I, so some will go up, some will go below the mean, so the overall effect of tau I should be, summation of tau I should be equal to 0. This is the constraint we had. Now we can solve for, so this is a plus 1 unknowns and a plus 1 independent equations, you can solve for the unknown parameters. Simple Ax equal to b equation, that is what we have, that is what I have written here. So the last equation is going to be tau 1 hat plus tau 2 hat tau a hat equals to 0. You can even remove the first equation because it does not make any sense. So, you have a plus 1 unknowns, a plus 1 equations including the tau a constraint. Now, you can solve for parameters, simple linear solution to linear equations, clear, and that is how we got the formula for every value, every equation, the ANOVA equation, right. So, that is why I said do not bring cheat sheet or anything because I will make you derive this, okay. So, this is what, now you have an estimate of mu hat which is y bar dot dot, this is my unknown, and similarly tau I hat equals to y I hat minus y bar dot dot, that is tau 1 hat is nothing but y1 dot minus y bar dot dot. You can simply estimate, solve it and get the equations. Make sense the linear regression approach to ANOVA, okay. So, of course, the solution is not unique, the solution depends on the constraint we have chosen because it is not straightforward a plus 1 equation a plus 1, we have put in a constraint that summation tau I equals to 0. For a random fx model this constraint is not valid, okay. There are two models, right, fixed fx, random fx. For a random fx non model this is not valid, we have a different constraint to solve it, okay. Only for a fixed fx model we have summation tau I equal to 0 and the solution will depend upon the constraint you have taken, clear, simple. Shall we move on, okay. So, there is, these equations are also called normal equations. I have told you when we did linear regression because you know the equation, set of equations you obtain by least squares is also called normal equations. Any idea why normal equation? Any idea why is this called normal? Every wording has a meaning. Why is it called normal equation? Have you ever thought about geometrically least squares? Geometric idea of least squares. Remember, what are we trying to solve in least squares? I mean, let us take a simple viewpoint. So, let us say I have y equals to mx, or you know in this case this is nothing but mu plus tau I, y hat equals to mu plus tau I hat, y equals to mu plus tau I plus epsilon ig, right. You remember we will not get exact equations to solve for because of the noise. I told you when we started, otherwise you will have a equations, a unknowns, you will say it forward, I mean you will have a data, n data points, n unknowns. You have n data points but lesser number of unknowns because of noise. The equations does not match. So, I told you when we started, you may have you know if I write it as y and x, you may have 4, 2, 4.1, 2 and 4.2 also 2, and you could have 8, 8, 8.1, 8, 8.2, but you could have 4, 4, 4. Why is this variation in y? Because of the noise. So, you will not have a unique solution, right. Now, I want y hat and y to be as close as possible, right, that is what I write it as y minus y hat the whole square. Square, is it a distance or not? What is your Euclidean distance? How do you measure Euclidean distance? Huh? What is Euclidean distance? How do you compute distance between 2 points using Euclidean? Huh? Square root of x2 minus x1 the whole square plus y2 minus y1 the whole square. So, squaring is what? This is actually distance squared. Your objective function is nothing but distance squared in a sense, you understand, it is a distance squared. So, all of them are related, if you start looking at it carefully it is actually a distance squared. Now, when will be distance between 2 points be minimum? When will distance between 2 points be minimum? Distance will be 0 when both the points are same, distance of a comma a equals to 0, right, clear. Now, I want distance of a comma b can never be 0 if b is not equal to a, that is a property of distance. distance of A by comma B cannot be equal to 0 if B is not equal to A. Now, but I want distance of A comma B to be minimal. When can that happen? When the points are perpendicular, right? When A and B are perpendicular, then what do we have? We have the distance to be minimum. So, what are we actually trying to do in least squares if you are to figure out? You want to find you cannot find y minus y, you cannot make the error 0 or the distance 0. So, you want to make the distance to be as minimal as possible. So, what will be y hat? What is y hat? It's an orthogonal projection of y basically, right? You understand? So, y and y hat should be perpendicular so that the distance is minimal. So, that is why we call it as normal equations. I will not get into projections etc., then it is a geometric meaning. So, I encourage you go through it to see what is the geometric meaning of least squares. It is basically projections, right, orthogonal projections. So, y minus y hat the whole square, we want to talk about y hat being orthogonal to y, is an orthogonal projection, and therefore we call it as normal equations. That is the reason why we refer it to normal equations. Make sense? Clear why we call it as normal? Because we know normal is what? Perpendicular and tangent and normal equations. So, that is why this is called least squares normal equations, okay, because of trying to figure out a orthogonal projection. So, because 2 points the distance is minimum when they are orthogonal, and we are only minimizing actually squared distance. If you take square root of y minus y1 the y2 minus y1 the whole square, this is nothing but square of distance squared, okay, clear. So, now in general if you want to do a regression, there are certain rules which you can easily follow to figure out the normal equations without having to do differentiation and expansion, okay. If you do differentiation and expansion, you may do some errors in differentiation, goof up. So, there are simple easy rules to actually write the normal equations. The normal equations, I meant this a plus 1 equations, you can simply write it out without having to differentiate using simple rules. This is applicable for any linear regression problem, okay. You do not need to even differentiate. Without differentiation you can write down the normal equations, clear. So, going forward I will not differentiate, I will use these rules to write down the normal equations, okay. So, rule number 1, there is one normal equation for each parameter in the model to be estimated. Whatever linear regression model you write there is one normal equation for each parameter. So, if there are a plus 1 parameters, understand there are a plus 1 equations. So, for each parameter there is one normal equation, that is rule number 1, simple. So, rule number 1 tells you how many normal equations are there for your model, it is equivalent to the number of parameters you want to estimate. And rule number 2, the right hand side of any normal equation is just the summation of all observations that contain the parameter associated with the particular normal equation. Let me repeat, the right hand side of the normal equation is nothing but summation of all the observations, the parameter is there wherever the parameter is there, all the observations that contain the parameter associated with normal equation. Suppose if you go back, if I want to write the parameter equation for mu hat, I want to write the parameter, I want to write the normal equation for mu hat. Mu hat is contained in how many data points? All data points. So, right hand side is what? Summation of all data points, that is what y dot dot is. You understand? If I want to write tau 1 equation for tau 1, tau 1 is contained in how many data points? Only first column, first row. So, it is y1 dot, n points, small n points. Similarly for y2 etc. So, the right hand side is nothing but a summation of all the observations that contain the parameter. So, that is rule number 2. So, rule number 2 helps you write the right hand side. Rule number 1 tells you the number of normal equations. Then we go on to rule number 3. The rule number 3 is about the left hand side. So the left hand side of any normal equation is summation of all model parameters, is summation of all model parameters, where each parameter is multiplied by the number of times, where each parameter is multiplied by the number of times it appears in the total on the right hand side. So the left hand side is nothing but summation of all the parameters. So go back, the left hand side is summation of all the parameters, mu hat plus tau 1 plus tau 2 plus tau 3 plus tau a, all the parameters. But what is the pre-multiplying term? The pre-multiplying term is nothing but it is each multiplied by the number of times it appears in the total on the right hand side. So y1, so if you go back, tau 1, how many times it appears in y dot dot? Tau 1, how many times it appears in y dot dot? Small n times, small n times there is tau 1. Tau 2, how many times it appears in y dot dot? Y dot dot is a grand sum. How many times tau 2 dot appears? Tau 2 appears small n times. That is why, and mu hat appears how many times? Now all the data points, that is a times n, which is capital N, right? You understand the third one? Now come to the second equation. Second equation is what? Mu hat plus tau 1 hat plus tau 2 hat plus up to tau a hat equals to y1 dot. That is the equation, because as per rule 3 you have the left hand side is the summation of all the model parameters. I have written all the model parameters, summation of all the model parameters, and it should be pre-multiplied by the number of times it appears on the right hand side. So the right hand side is y1 dot. How many times mu appears in y1 dot? Small n times, because total data itself is n only, small n times. How many times tau 1 hat appears in y1 dot? Small n times. How many times tau 2 appears in y1 dot? Tau 2 and y1 hat are not related, right? So it is 0, and similarly up to 0. So that is how you get the second equation. You can apply it to any of these equations, so you will get all the a plus 1 equations. Just the 3 rules. The first rule is simple, each equation is for every model parameter has one normal equation. The second rule says simply the right hand side of the normal equation is the summation of how many times the model parameter has appeared. It is basically summation of all the observations that contain the model parameters. So if you take mu hat, it appears capital N times. So summation of all the observations yij, summation of double summation of yij, which is y dot dot. Tau 1 hat, if you want to write for tau 1 hat, tau 1 hat appears in how many equations? Only in the y1 dot, right? It is summed only for first row. And similarly tau 2 hat, if you want to summation of all the observations, summation of all the observations is what? Y2 dot, y3 dot, y4 dot. That tells you about the right hand side. And what about the left hand side? The left hand side, rule number 3 says it is summation of all the parameters. So write out all the parameters, summation of all the parameters. Then start pre-multiplying. The pre-multiplying term is nothing but the number of times it appears on the right hand side. So if you take y dot dot, mu hat appears capital N times, tau 1 appears small n times, tau 2 appears small n times. So that is how you get the first equation in ANOVA. And in the second equation, your right hand side is nothing but y1 dot. Okay, how many times mu appears? Small n times. This, remember, this is y1 dot, only first column, first row. And then mu 2, sorry, tau 1 and y1 dot n times, small n times. Tau 2 and y1 dot, it will not appear because you are talking only about first row. So the pre-multiplying term is 0 for other treatment topics. That is how you get the normal equations. You do not need to differentiate at all, you will get the normal equations, a plus 1 normal equations. Clear? Everybody? So far so good? Agreed? So now we start talking about R square statistic, right. Remember we simply state R square statistics is what? The variable, the variance explained by the model divided by the total variance. If you multiply by into 100, you will get the total, but still I have only estimated, if you look at, I have only estimated the what I call the mu hat and tau 1 hat. I did not give you the equations for sum square error, sum square total and sum square treatment. Somebody asking me for sheet, probably they meant that because when they want to apply ANOVA, I have asked you to remember the formula, okay, but we will actually derive it here, okay. So we will do what is sum square treatment, how do I estimate sum square treatment as sum square mean, sum square total and sum square error, okay. So let us talk about now the R part, the variance explained by fitting each and every parameter, okay. The total variance explained is nothing but the variance explained due to parameter mu and parameter tau I, right. Remember this should be high, the R value should be high, otherwise your model is bad, okay. So we start talking about R mu comma tau. What is this? This is the variance explained due to what? Due to fitting the model. How do I write this? How do I have this R mu comma tau? How do I write this? The total variance is what? So this is what is mu hat. So this is multiplication of actually the mu hat into y double dot, tau 1 hat into y dot dot, y 1 dot plus tau 2, this is the total variance, okay. Always the summation of the parameter estimates each multiplied by the right hand side of the normal equation. So the total variance, if you want to understand what is explained due to the model, that is also simple, multiply the right hand side with the parameter, corresponding parameter, because that is what, why is it the variance, that is what the number of times it has appeared. So mu hat has appeared in all the observations, so that is why it is y dot dot, mu hat into y dot dot gives me the variance explained due to fitting the model mu hat parameter. Tau 1 dot, what is the variance explained? Tau 1 dot, how much tau 1 if I fit variable, what is the variance explained? It is tau 1 hat into y 1 dot. Why it is tau 1 hat into y 1 dot? Because tau 1 is appearing only in those many terms. So the total variance is nothing but thus multiplied by the summation of those observations, and tau 2 is what? Tau 2 hat into y 2 dot, that is the variance explained, okay. So the total variance is explained as what? Mu hat into y double dot, that is the parameter multiplied by its right hand side in the normal equation. Why is that making sense? Because mu hat appears in all the equations, so if you fit mu hat it should explain more variability. So that is why mu hat into y double dot plus tau 1 hat into y 1 dot plus tau 2 hat into y. This is my total variance. So I simply write it as mu hat into y double dot plus summation I equals to 1 to a tau I hat into y dot. Remember I know what is mu hat. Mu hat is, I have estimated, this is nothing but y bar dot dot, and what is tau I hat? Tau I hat I have estimated again using the normal equations, this is nothing but yi dot minus y bar dot dot. This is what I have estimated after solving for a plus 1 equations, okay. So this is my total variance explained by the model. Now I can derive for sum squared error, sum squared treatment, etc. What is sum squared error? What is sum squared error? The total variance minus the variance explained, that is a sum square error, right. The total variability in the data and the variability that is due to the model, if you subtract both, then you will get what is remaining, which is nothing but your sum squared error. So what is the total variability in the data? Yij squared, double summation Yij squared is nothing but my total variability in the data, and minus r mu comma tau should give me the, so summation Yij squared minus r mu comma tau should give me the sum squared error. So this is my sum squared error, clear. So I can expand on remember these are my estimates after applying the constraints. So I can substitute for mu hat and I can substitute for tau I hat and I can get what is known as r mu comma tau. This is simple simplifications, right. I know what is mu hat, I know what is tau I hat, I just simply substitute it, right, simply substitute it. So this is my r mu comma tau, and now I have an equation for sum squared error. If you go back and look, this is what you will have, sum squared error equation, okay. When you, so I do not want you to remember anything, we can derive each and everything, okay. So this is your sum squared error, and the degrees of freedom we have already discussed, okay. So the degrees of freedom we have already discussed, it is going to be a into n minus 1, which is nothing but a n minus a, that is nothing but n minus a degrees of freedom, okay. We discussed in the ANOVA what is the degrees of freedom. So the degrees of freedom is a into n minus 1, there are a treatments, for each one you have one mean, so n minus 1, so a into n minus 1, a into n minus 1 is a n minus a, which is n minus capital N minus a degrees of freedom. So this is my sum squared error equation, okay. So now I can figure out the what I call individual parts, okay. So I can figure out individual parts alone, meaning what is the effect of adding mean, what is the effect of adding tau. So two parameters I have fit, right, are a plus 1 parameters. What is the effect of adding mu alone? N mu hat, remember. So what is the effect of r mu? R mu is nothing but mu hat into y double dot, multiply with the right hand side. What is mu hat? Mu hat is y bar dot dot into yi. So the total variability that is explained by fitting a mu as the only parameter is y dot dot square by n, that is only variability explained by mu. And what is the variability explained due to tau I alone? That is nothing but full model minus reduced model minus r mu. So this is my r tau given mu, this is variability explained by tau, right. I am looking at two parameters, two a plus 1 parameters, that is mu and tau I, these are the parameters I fit. So what is the variability due to mu alone? R mu is nothing but mu hat into right hand side, which is y dot dot. So mu hat is nothing but y dot dot bar, that is the estimate. So I know what is r mu, which is nothing but y dot dot square divided by n, okay, because what is y bar dot dot? Y bar dot dot is nothing but y dot dot divided by n, okay. So now I have y dot dot divided by n into y dot dot, which is equals to y dot dot squared by capital N. This is my variability explained due to mu alone. And what is the variability explained due to tau alone? That is nothing but total variability minus variability due to total variability explained minus variability due to mean mu. So the variability explained, total variability explained, I have this equation r mu comma tau and minus r mu, that will give me the variability due to fitting of tau I. So we have looked at individual variabilities explained, okay. Total variability explained r mu comma tau, then we know what is r mu, then we know r tau given mu, okay, that is the variability explained due to fitting tau I, right. So now what do we have? We say when we do null hypothesis or when we do this hypothesis testing in ANOVA, what do? We want to know whether treatments are significant or not significant. Then what should be that? This should be nothing but variability explained due to tau divided by what? Error, right, that is what we have. So variability explained due to tau is nothing but r tau given mu, and what is the degrees of freedom? It is divided by a minus 1 degrees of freedom. And what is the sum squared error? I have derived the sum squared error, this is my sum squared error. And what is the degrees of freedom? A n minus 1 or n minus a, this is my f statistic we are using. Now you understand bit by bit of ANOVA what we are doing. We are now really seeing in terms of least squares what we are seeing, whether the variability explained by the treatment, fitting of treatment, is it significant with respect to the variance, unexplained variance. If your unexplained variance, and if your treatment variance due to fitting a treatment, if they are same, what does it mean? Your treatment has no significance, right. Your variance explained, variability in the data explained due to fitting a parameter should be far higher compared to the unexplained variance. The overall idea is what? Your unexplained variance should be as small as possible, that is your sum squared error should be as small as possible, and the variability explained by the treatment should be as large as possible. That is why we take a ratio here. Now you understand what does actually the ANOVA model does. The ANOVA simply models looks at R explained by the model divided by R unexplained, that is what it is, clear. So in this process we have derived everything. There I have given it as formulas, sum square treatment and sum square total, I have given it as formulas and asked you to do it, but here we have exactly looked at the problem. So we wrote the normal equations. So what did we do? A quick recap, we wrote the normal equations just by differentiation. So we could simply do a differentiation and it will result in a plus 1 equations, okay, and you cannot solve a plus 1 equations, a plus 1 unknowns, because all these a plus 1 equations are not independent. There are only a equations which are independent, and therefore you use the constraint that tau ij equals to 0. Remember summation tau ij equals to 0, remember depending upon the constraint you use the solution will vary. This constraint is only for a fixed fx model. For a fixed fx model we said summation tau ij equals to summation tau I equals to 0, then we use those constraints and figure out the equation parameters, and we looked at an easy way to do it using 3 rules. The total number of equation, rule 1 is total number of equation is equal to total number of model parameters. So the right hand side is nothing but summation of the observations that contains the parameter itself, and the left hand side is nothing but summation of all the parameters pre multiplied by the number of times it appears on the right hand side. So if I just apply these 3 rules, I will get all the a plus 1 equations or whatever number of parameters required, number of equations required, you will get those normal equations. We also called it as normal equations, I explained to you why, because we are only minimizing the distance between y and y hat, and the minimum distance is nothing but always a orthogonal distance, and that is why we call it as normal equations, okay. And then coming back, once we got the estimate of the parameters using these normal equations, then what did we do is we wanted to look at the variability explained, that is a key factor in your linear regression. So the variability explained due to the total model is nothing but the parameter multiplied by the right hand side of the normal equation, that is what we did, okay. So and then I expanded, I got r mu comma tau, I can also get r mu which is y dot dot square divided by capital N. Then the variability only due to treatment is nothing but subtraction of both those terms, and that is what I had subtraction of both these terms, clear. And then sum squared error, I can get an estimate of sum squared error. The sum squared error is nothing but the total variability minus variability due to the model, that is my sum squared error. So truly what do I want to now check in treatment in ANOVA? I want to check what is the variability explained by the treatments compared to that of the unexplained variables, that is what your F distribution is. That is nothing but r tau given mu divided by a minus 1, because there is a minus 1 degrees of freedom, and you know that total no treatment variability explained be divided by unexplained variables. The unexplained variance has a degrees of freedom of a into n minus 1, which is capital N minus a, clear. So this is the overall ANOVA in a nutshell. I wanted to finish least squares and come back. So now you understand ANOVA the whole circle, every bit by bit we can do it, clear. And I have given you in the first ANOVA class, I have derived expectations of sum squared error, sum squared total, sum squared treatment, so that what it converges to, that is a different viewpoint, and this is a different viewpoint from a linear regression.